This thing has no battery, no circuit board, no USB part, and no smart chip. It runs on a piece of fabric and some liquid fuel, and it hasn't needed a single update in over 100 years. But here's the thing, when I picked this up in an antique store, I didn't see an antique. I saw something I already knew. So, let me back up. It's leaking and I don't want to burn the place down. So, I turned it off. I was walking through this antique store, that kind that smells like an old wood or somebody's grandmother. I was just browsing, not looking for anything specific. Then I saw it, sitting on the top of the shelf between a broken clock and a ceramic cat, a kerosene lantern. Now, most people look at this and they see a decoration, something you would put on a farmhouse shelf or use it as a Halloween prop. But the second I saw it, something else happened. Growing up, my parents used one of these, not as a decor, as actual light. So when I picked it up, I wasn't thinking about the price tag. I was thinking I never actually understood how this thing works, and that bothered me because look at it, there's almost nothing here. It's just a metal tank that holds the fuel, and the wick is just a braided cotton, and a collar that adjusts the height of the wick, and the glass chimney sitting on top. That's it, no moving parts, no electronics, no engineering degrees required. And yet this design powered the entire world before electricity existed. Hospitals, homes, mines, streets, all of it running on this. So today we are going to take apart conceptually and figure out exactly what's happening inside this flame. And I promise you by the end of this video you are going to look at fire completely differently. Alright, let's start at the bottom, which is right here, where the kerosene fuel sits. The fuel, kerosene, sits down at the reservoir, which is right here, and the wick sits inside it, with the top end sticking out in the air where it burns. Here's the first question that should bother you. How does a flame get from down here all the way up to the flame? Because gravity exists, and liquids don't climb upward on their own. Or do they? Here's a little experiment. Let me show this close. It's wet. I'm not squeezing, I'm not pumping, I'm not doing anything. The liquid just climb on its own. It's called capillary action, and it's the same force pulling kerosene up through your wick right now. Here is what's actually happening. Water and most liquids have something called surface tension. Think of it like the liquid has a very thin elastic skin on its surface, now inside a narrow tube, or in this case the tiny fibers of the wick. That skin interacts with the wall of the tube. The liquid actually sticks to the material, and now because the tube is so narrow, the sticking force is strong enough to pull the liquid all the way up against gravity. The thinner the tube, the higher it climbs. So the wick isn't just sitting there and being passive. It's an active pump, a passive active, that runs entirely on molecular physics, zero energy required. The fuel is literally being pulled upward toward the flame by the same force that makes trees move water from their roots to their leaves 100 feet above the ground. The same physics, completely different scale. This glass globe isn't protection, it's an engine. Okay, this is where it really gets interesting. Most people assume that the glass is just a windshield, something to stop the flame from blowing out. And yes, it does that. But that is the least thing interesting this thing does. Look at the flame without the chimney. It's unstable. Flickers, dances. Now watch, let me put the chimney. It's not just protected now, it's stronger. Wonder why? The chimney creates a draft. Let me put that aside. When the flame burns, it heats the air around it, and hot air is less dense than cold air, which means it rises. Now that rising air has to go somewhere, so it flows up and through the top of the chimney. As it leaves, it creates low pressure air zone at the bottom, which pulls fresh air, cold air from underneath. The incoming air brings oxygen. More oxygens mean a stronger, more complete burn, which makes the air hotter, which makes it rises faster, which pulls in more cold air from the bottom. It's a self-reinforcing loop. The chimney doesn't just protect the flame, it feeds it. It turns a wobbly candle into a combustion engine. And the shape matters too. The slight taper at the top. That's not decorative. An air exit means the air velocity increases at the top, like squeezing a garden hose, which strengthens the draft even more. Whoever designed this understood fluid dynamics long before there were a textbook on fluid dynamics. Why is fire that color? The answer connects to the sun. Now look at the flame itself, that orange-yellow glow. You probably assume that's the color of kerosene burning, or the color of the wick burning. It's neither. That color is coming from something much more interesting. When kerosene vaporizes and burns, the combustion isn't perfectly clean. Teeny tiny particles of carbon, basically microscopic soot, from inside the flame. These particles get incredibly hot. We are talking over 1,000 degrees. And here's the physics. Any object hot enough will glow, not because of chemical reaction, but simply because of temperature. The hotter it is, the more light it emits. And the color of that shifts from red to orange to yellow to white as the temperature increases. And this is called blackbody radiation. And those tiny soot particles inside the flame, they are glowing orange-yellow because that's exactly what carbon does at exactly that temperature. Now here's the part that should make you stop for a second. The same physics, the exact same equation that describe why the sun, the color it is. The sun glows the way it does, not because of its chemistry, but because of its temperature. The yellow-white light coming from 93 million miles away. The same mechanism as these soot particles. The physics is identical. My parents didn't know any of this. They weren't thinking about capillary action when they filled up the fuel tank. They weren't thinking about convection and airflow when they adjusted the wick height. They were just trying to see in a room with no electricity. But the physics was there the whole time, working perfectly every single night. Capillary action, pulling the fuel upward, convection, turning the chimney into an engine, blackbody radiation, turning hot carbon into light. All of it in this simple object that a child could pick up and a physicist spend a career analyzing. When I picked this up in that antique store, I thought I was buying a memory. It turned out I was buying a physics lesson. If you want to see what happens when I apply the same principles to something more extreme, click subscribe.